Yeah. So let's start with this 5 by 5 matrix A. Yeah. So we want to find the Jordan form of this matrix. Yeah. So what will be the Jordan form for this matrix? Can anyone guess? And then I'll proceed. Yeah. So first you make a guess what it will be, and then we can proceed to prove that it is indeed that. Yeah. So what will be the Jordan form? How will it look like?
Diagonal matrix.
Diagonal matrix, yeah. So it is going to have 5 blocks, yeah, each of size 1 by 1. So this we started with a relatively simple situation. Yeah, I made this large, but now I am not able to make it small. Yeah. Okay. Good. So the reason why it is diagonal is it has 5 distinct. It's a 5 by 5 matrix, and the characteristic polynomial is so. So if you look at the characteristic polynomial of A, it has 5 distinct roots. Yeah, e minus 1 to e minus 5. Right. So as soon as it so this we also saw that anything like this is diagonalizable. Yeah. So anyway, if you look at it has 5 eigenvalues, so it has to have each eigenvalue has to have eigenspace at least dimension 1, and total dimension is 5. So that tells you that each eigenspace is one dimensional. Yeah. So in various ways, you can see that is diagonalizable, and the Jordan form is precisely 1, 2, 3, 4. So diagonal matrix is already in Jordan form, right? So this is the Jordan form of this 5 by 5 matrix. So I mean, you don't have to do any operations on the matrix. Yeah, just by looking at the matrix, you can. So I mean, that means. So let's call this B, or let's call this J for Jordan, or JA for Jordan form of it. So we know that there exists P such that P inverse AP is J. Yeah. But if you have to do it manually, you'll have to do some row operation and corresponding column operation, right, to get this conjugate. So if you wanted to do it manually, so if you did it manually, the advantage is you get P as well, because the row operation, column operation tells you what matrix you are multiplying as well, and pre-multiply. So but I mean, if though I can tell you what the Jordan form is, this doesn't tell you what the matrix P is. Yeah. So the matrix P is usually difficult to figure out, but the Jordan form maybe you can figure out by other tricks. Yeah. So using for instance the characteristic polynomial, or we'll see the minimal polynomial and so on. Yeah. So let's do some other example before. Yeah. So instead of here the characteristic polynomial was product of 5 distinct linear factors. Yeah. So let's stick to this 5 by 5 matrix, but instead of this matrix, maybe we assume that our matrix is somewhat different. Yeah. So that the characteristic polynomial is not doesn't have 5 distinct roots. Maybe it has only, let's say, 2 distinct roots. Yeah. So let A be such that CHA T is let's say T minus 1 times. So some powers also I'll have to put, yeah. T minus 2 and total degree has to be 5, right? So yeah, so maybe let's put 3 and 2. Right, so suppose it's something like this. Or let's see, is there some examples I'm doing? This. So I'll do maybe the simpler case first, where there are three factors, three distinct factors, and the more complicated one we'll do in a bit. Yeah, two factors in a bit. So suppose you are in this scenario. Yeah, characteristic polynomial has to be of degree 5, and you can factor like this. So this can happen, right? So if I replace here 2 by 1 and maybe maybe if I replace this 5 by 1 and this 4 by 2, then we will have this scenario. Yeah. So if I replace this, so I mean, you can take this matrix. Yeah, 1, 1, 2, 2, 3, and you can fill out some numbers here. Right, and zeros here. So you can fill out whatever numbers here, and then if you look at the characteristic polynomial, you get this. Yeah. So then, of course, there are many possibilities. Yeah. So what are the possibilities for Jordan form? So what are the Jordan? Which Jordan block you can determine? Yeah. So for which eigenvalue you can determine the Jordan block? Let's start with that. Three, right? So the point is, if you look at the three has comes with multiplicity 1, yeah. So minimal polynomial of this matrix A is going to be something, but the factor t minus 3 will be there, but you don't know whether I mean whether it will be this exponent and this exponent, you don't know, yeah. So whether let's call it, let's give this some number, yeah. Let's some variable A and B. So A and B you don't know. It could be 1 or 2, but the power of t minus 3 we know it's going to be 1. Yeah, it can't be 0 because the characteristic and minimal polynomial. Sorry, our notation was P, right? So let's stick to this. Minimal polynomial. Yeah, so t minus 3 has to divide PAT, and characteristic polynomial and minimal polynomial divides characteristic polynomial. So the exponent of this is yeah. So as soon as we know that the minimal polynomial, and we know, so if you look at V3, yeah, so V is so it's acting on V is what? V is C5. So our matrix is acting on so field of complex numbers with sorry, on vector space of 5-dimensional vector space of complex over complex numbers, right? So column vectors of length 5. So if we try to figure out the generalized eigen space of for 3, we know that it is going to be one-dimensional, yeah. So in fact, one of the homework problem tells you that the characteristic polynomial of yeah. So maybe this is how I can. So CH of let's call the endomorphism which A defines as phi A. okay, on V. Then if I restrict it to V3, this has to be T minus 3. Yeah. So that tells you that V3 has to be one-dimensional. This implies V3, a dimension of V3 is 1. Yeah. So the only possibility is J3 must be, it has to be J3 1. Yeah, one of the blocks has to be J3 1. J3 1 is a block, is a Jordan block. Yeah, so one of the Jordan block is J3 1. So it's a 1 by 1 matrix with entry 3. Yeah. Now one has to decide for 1 and 2. Yeah. So the point is, it's sort of difficult to decide for, meaning it depends upon the matrix. Yeah. Um, but you can figure out still. Yeah. So whether I mean, you'll have to do some calculation with the matrix, but not too many. Yeah. So what you do is you look at A minus 1. A minus, so you want to figure out the generalized eigenspace, dimension of the generalized eigenspace for or maybe first the eigenspace. Yeah. So you consider A minus 1, I. So A minus I will acts on C5. You can look at the null space of this. Yeah. So you know what the null space is V such that A minus IV is 0, V in C5. Okay. So this we know that is going to be at least one-dimensional because this is one is an eigenvalue. Yeah. So so uh, so there are two possibilities: one-dimensional or two-dimensional. Yeah. So so the to figure out, how do you figure out the dimension of the null space of A minus I? From the matrix. So you have the matrix A minus I. How will you figure out the dimension of the null space? This 5 by 5 matrix. So, I mean, you'll have to figure out the rank of the matrix, 5 by 5 matrix. So you know that the rank is at most 4 because, I mean, you look at this, for instance, this is your A. When you subtract I, then this becomes, I mean, rank is at most 4 because you know that this null space has dimension at least 1. Yeah. So then to figure out whether it's 1 or 2, it can't be more than 2 as well. That also you can argue. Yeah. So if you can find, if you can show that the rank is less equal 3, then um, so you can somehow show that the rank is less than equal to 3, then it has to be 3. Okay. And so if the rank is 3, then the null space has rank plus nullity theorem, rank nullity theorem you can use. So you can figure out the rank of the matrix somehow. Yeah. So by maybe row operations or column operation, a little bit of calculation you'll have to do, or calculate some 4 by 4 minors, for instance, of A minus I, and see if if some 4 by 4 minor is 0. Yeah. Then so all 4 by 4 minor must be 0. In fact, if the rank is 3, then all the 4 by 4 minors must be 0. And if one of the 4x4 minor is non-zero, then the rank must be 4. Yeah, so you just check with one 4x4 minor and see if the check the determinant. Yeah, and you'll figure out. So one can do a little more calculation and figure out the two situations. Yeah. So if it is one dimensional, that if the null space is one dimensional, but this will only give you. So okay, one dimensional will not tell you exactly what the situation. Yeah, so it will tell you both the situation. So if the null space is one dimensional, what does that tell you? That the the space of eigenspace has dimension 1. Yeah, and what should be the dimension of the generalized eigenspace? The generalized eigenspace should have this dimension, this exponent, because the generalized the characteristic polynomial of the generalized eigenspace is for 1 is of degree 2 and for 2 is degree 2. Yeah, so the dimension of the generalized eigenspace is 2 or, for both of them. Yeah, so note that by what we have seen, dimension of V2 is a 2 and the dimension of V1 is also 2. Yeah, so these are generalized eigenspaces. Yeah, so maybe generalized 2 eigenspace. And this is generalized 1 eigenspace. So that we know is both of them is 2. And this null space tells you what will be the dimension of the eigenspace. Yeah, not the generalized eigenspace, but eigenspace will be smaller, right? So eigenspace has dimension 1 or 2 depending upon what the dimension of this thing is. Yeah. So there are two cases. Yeah. So let's say E1 is the eigenspace, one eigenspace. E1 is contained in V1. This is one eigenspace. And E2 contained in V2 is the 2 eigenspace. Yeah. So that there are various possibilities. Yeah. So let's see. So whether for to determine the dimension of the eigenspaces E1 and E2, you'll have to do this calculation. Yeah. So that will depend upon the matrix, but it's a smaller calculation than computing the whole of P. Yeah. So that one can do by looking at the matrix a little bit. So there are two cases. Dimension for dimension E1, there are two cases, and dimension E2, there are two cases. Yeah. So the two cases are, this is 1, 2, and yeah, so so total there are 4 cases. So I'll have to draw some. Yeah. So maybe I'll have to send this further down. Yeah. So so 1, 2, 1, 2, and this is dimension is 1, 2, or maybe even dimension. So in these two cases, the dimension is 1, and in these two, it is 2. Yeah. So it's possible that dimension of this is 1. This has dimension 1. This has dimension 2. This is dimension 1, and so on. These are the 4 cases you will get. Right. Okay. So now in these cases, what are the Jordan blocks going to look like? Yeah. So if dimension of So say dimension of E1 is 1. Yeah. So there is only one one dimensional eigen space. Then what does the minimal polynomial look like? So maybe you can sorry. So yeah. So in this case, maybe yeah. Yeah. So there are 4 cases, and I want to figure out everything in these 4 cases. PAT. Yeah. So of course, t minus 3 is a factor. What else? What will be the minimal polynomial in this case? T minus 1 and I mean it can't be there. So total I mean it has to be it has to have 3 distinct factors at least. Yeah. So it can be it has to, and you'll have to tell me what A and B are. Yeah. So what should be the exponent of t minus 1? A and B, we know it has to be 1 or 2, right? So in 1 case, what should it be? Yeah, say it louder. How many of you think it's 1? Maybe there are only 2 options, so I can take a poll. No one thinks it's 1, and how many of you think it's 2? 2 of you, and what about the others? They are not sure. Yeah, so it is 2. Why is it 2? See, the t minus 1 will not annihilate v1, right? Because I mean v1 it will annihilate only e1 because e1 is the eigenspace. Yeah. So t minus 1 will not annihilate whole of v1 because e1 is different from v1. Right. So you'll have to at least square it to make sure it, and as soon as you square it, it will annihilate because I mean the characteristic minimal polynomial has to I mean, it has to have factor. It has to be at the b. If it is not 1, it has to be 2, right? Because this v1 has dimension 2. Yeah. So that is the reason it cannot be 1. It has to be 2 because t minus 1 cannot annihilate e1. It can only annihilate. It cannot annihilate v1. It can only annihilate e1. And so that's how this minimal polynomial is sort of determined by just knowing this. So in this case, it will be t minus 3, t minus 1, and t minus 2 whole square. Yeah, because now in this case, E1 is equal to V1. So t minus 1 will annihilate. So if you restrict A to this V1 itself, phi A to V1 itself, it will be annihilated by just t minus phi A minus identity. Yeah. So you get that PAT is this, and in this case, in the third case, it will be t minus 3, t minus 1 whole square. So because E1 has dimension 1, and this is t minus 2. Yeah, and in the third case, it's t minus 3 times. So they both as in this last case, both eigenspaces are equal, are same as the generalized eigenspace. Yeah. So you get this. Okay. So now how does the Jordan form look like in these cases? So let's start with the last case. What will be the Jordan form in this case? Diagonal matrix. Yeah. So because I mean you can also check by dimension of the eigenspaces. Yeah. So this has it has a basis of eigenvectors, for instance, right? There is a 3 eigenvector and 1 eigenvector. There are 2 independent ones and 2 eigenvector. There are 2 independent. So this will give you diagonal. Yeah. So it will. So the Jordan form will look like 1, 1, 2, 2, 3. So is this clear? Yeah. How about in this one? What will be the Jordan? How will the Jordan form look like? So again, so of course, and the rest maybe even can figure out slowly. So this, yeah. So in second last one we are doing. So three, there is only one 3 block. What about the 1 block? How does 1 block look like? So it can't be diagonal, right? If it was, I mean, because t minus 1 square you need, yeah. So what you I mean, generalized eigenspace looks like is a truly generalized eigenspace. It's not an eigenspace. So you would need something like this to kill it, yeah. So it will look like this, and then they will since two. So you can take a basis of E2, any basis of E2, and it will give you this. Yeah. So what you'll have to do is you take so the basis you are taking is take eigenvector 3 eigenvector, any non-zero 3 eigenvector, to take 2 linearly independent 2 eigenvector. Yeah. Which you can do because E2 has dimension this dimension 2, and for and to get a basis of V1, what you do is you take because see your minimal polynomial is t minus 1 square. Yeah, so there is a vector which is a generalized eigenvector but not a eigenvector. So in fact you take um, you take such a vector essentially and it will work. Yeah. So if you apply a minus I to it, it will not become 0. But when you apply a minus I whole square to it, it will become 0. So the basis is that a generalized eigenvector which is not an eigenvector, and then a minus I times that that vector. Okay. So here for this one, to get this, I'm just trying to tell you what is the basis. So we know that the C5 we can decompose it as V1 direct sum V2 direct sum V3. Yeah. So V1 V2 V3 is clear. Yeah. For V1 we'll have to figure out. So take so you start with E in V1 minus E1 because there is something in there, and so that gives you a one non-zero vector of V1, and then you apply a minus I U E. Yeah. So of course this is non-zero because E is not an eigenvector. Yeah. And these two together is a basis of V1. Okay, so this we already saw. So it's that these are linearly independent. Yeah. So this is a basis. So if you take this basis, a basis of V2 and a basis of V3 together, this will give you a basis of V, and that if you write down A with this linear map with that respect to this basis, you'll get this this matrix. Yeah. Is that okay? So that tells you how it will look in this case. And similarly, in this case, you just interchange 1 and 2 and you'll get it. Yeah. And in this case, you'll get, say there will be 3 Jordan blocks, 1 for 3, 1 for 1, and 1 for 2. Yeah. Is this example clear in this whole setup? Yes. Yes. No. So from this observation, we can figure out something. Yeah. So first observation is this this result which I've written. So if the minimal polynomial of A is product of linear factors with no repeated roots, then A is diagonalizable. Okay. So how will you prove this? Let's try to. So this is, I mean, in this example, it is clear, but how will you prove this in general?
Since the minimal polynomial is a product of linear factors, we have that the dimension of the eigenspace with respect to every eigen value is the same as the multiplicity in the characteristic polynomial.
Yeah, that is. So you look at the characteristic polynomial of A, it looks like some t minus lambda 1 to power m1 to t minus lambda r power mr, and minimal polynomial will look like, because it has distinct factor, it tells you it is going to be t minus lambda 1 to t minus lambda r. Yeah. So now if you look at lambda 1 eigenspace, so let's say E lambda 1, E lambda 2, and E lambda r. The fact that the minimal polynomial is product of linear factors, that tells you that E lambda 1 is the generalized eigenspace as well. Yeah. So yeah. So yeah. So maybe so say so A is say n by n. Yeah. A is n by n. Then Cn, you can write it as V lambda 1 dxm V lambda r. And so we know that the minimal polynomial of this endomorphism A. Yeah, so so maybe let's not so let's discuss it. These are generalized eigenspaces. Yeah. So now so there may be other no. So there may be more. Yeah. So you look at phi A restricted to V lambda 1, and look at the minimal polynomial of phi A. This is this is just going to be t minus lambda 1 by what we proved last time. I mean, this version for characteristic polynomial is a homework. For minimal polynomial, we proved this, right? So so that tells you that phi A when restricted to V lambda 1 is just multiplication by lambda 1 on whole of V lambda 1. So that so this tells us that phi A restricted to V lambda 1 is lambda 1 times identity of V lambda 1. Right? So it's multiplication by lambda 1. So this implies that so you apply it to all. So this is true for all lambda. So maybe put I everywhere for all I between 1 and r. So this tells you that so you can use all the results, and this tells you that A is diagonalizable. Yeah, so it's a bunch of lambda 1s, then bunch of lambda 2s, and so on. Is this okay? Or in other words, V lambda 1 is a lambda 1 eigenspace, not just the generalized eigenspace, but lambda 1 eigenspace. So so there are no eigenvector of exponent 2. Everything has exponent 1. And so you can find a basis of eigenspaces, eigenvectors, for instance. Is this okay, everyone? So we saw that, I mean, of course, if the characteristic polynomial has all distinct roots, then of course minimal polynomial will also have all distinct linear factors with no repeated roots. Yeah. So that was the special case which we saw earlier. Yeah, that in that case it's a diagonalizable matrix, but this is a stronger result. So in fact, it's a characterization. Yeah, as soon as minimal polynomial has exponent more than for complex numbers, at least this is a characterization. Yeah. So as soon as the minimal polynomial has exponent more than one, it can't be diagonalizable. Yeah, because I mean it's similar to a Jordan form. Yeah, and the Jordan form is not going to be a diagonalizable. Yeah, so it is a characterization of diagonalizability. This one. Okay. So we showed that if it is the minimal polynomial has linear factors, then it is diagonalizable. And of course, if it is diagonalizable, then you look at the minimal polynomial doesn't depend upon the matrix. It only depends upon the equivalence class. Equivalence class of matrix up to similarity. Yeah, so you look at the diagonal form, and of course, in that case, you can see that the minimal polynomial is I mean, for a diagonal matrix, the minimal polynomial will have no repeated roots, right? So if I look at, for instance, this diagonal matrix, we know that t minus 1 times t minus 2 times t minus 3 will annihilate this matrix. Yeah. Is that okay, everyone? So this thing is actually a characterization. So maybe I'll write converse. Converse is easier, so that's what converse is trivial. So the non-trivial part is, so of course, if it is diagonalizable, then the matrix, then the minimal polynomial is product of linear fact is just an observation. Yeah. And the converse is also true and is trivial. Okay. Okay, so this was the case when there were three roots. Yeah. So here there are cases when there are two roots. Yeah. So maybe one can analyze these examples. So A is a 5 by 5 matrix, and minimal polynomial looks like t minus 1 whole square. So suppose the minimal polynomial is fixed, is t minus 1 whole square, t minus 2. And the characters, then there are many possibilities for characteristic polynomial. Yeah. So this is the one I thought of analyzing when I was preparing this. Yeah. So let's try to analyze what the Jordan block will be in this situation. Yeah. So suppose minimal polynomial is t minus 1 square times t minus 2, and their characteristic polynomial is t minus 1 square times t minus 2 whole cube. Yeah. Then in this case, what will be the Jordan? What will Jordan form look like?
2 cross 2 eigenvalue 1 block, and
so J21 you are J12 you are saying, yeah?
J12 and then J21 friends.
J21 3 blocks, yeah? This is what you're saying? So is everyone convinced that this will be the answer? Yeah, because the minimal polynomial, I mean, the one eigenspace has dimension 2, and as generalized one eigenspace has dimension 2, and one eigenspace cannot be dimension 2. Yeah, because you have to do t minus 1 whole square to annihilate it. So you need J12. and then the rest is J21 because T minus 2 annihilates it. Yeah. So the eigenspace, two eigenspace and two generalized eigenspace are same. Okay. How about in this case? If the characteristic polynomial is T minus 1 whole cube and T minus 2 whole square, that's possible, right? Because minimal polynomial is dividing the characteristic polynomial. So this is possible. In this case, what will be the Jordan block? So again, by the same reasoning, there are two, the generalized eigenspace for 2 is two-dimensional, and T minus 2 is the factor. So J2 is going to be, there are going to be J21s, yeah, two J21s, right? And what happens to this? So we will have to get a 5 by 5 matrix, yeah. So how will the J1 blocks look like? Can it be J13? Let's think about that. So there are various possibilities. It could be J13, right? Or it could be, so I will have to fill out this 3 by 3 block, yeah? So there are many possibilities. So J13 is one possibility. J11, J11, J11 is the other possibility, and the third possibility is J12, J11. Yeah. So these are the three possibilities we'll have. So which one should we put? Last one. Yeah, because it's, anyway, the minimal polynomial is T minus 1 whole square. Yeah, so it can't be J11. So this you can rule out. Yeah. What is the minimal polynomial for J13? So J13 looks like this. Yeah. This is how it looks like. So what is the minimal polynomial for J13? So you should look at T minus 1. So you subtract identity from it, yeah? So if you remove identity, so J13 minus identity is 0, 0. So it has to be a power of T minus 1, right? We want to figure out which power, yeah? So which power of T minus 1 will kill it? So, one power certainly doesn't kill it, that we know. Will T minus 1 whole square, what is T minus 1, J1 3 minus I whole square look like? Is it 0 or non-zero? So you can try to do this computation and see what you get. So what are you getting if you square this matrix? So it's non-zero, right? You get 1 in this extreme diagonal, extreme corner. Yeah. So T minus 1 square is not going to annihilate this. So the minimal polynomial is going for J1 cube is T minus 1 cube. Yeah. But here when restricted to this to one eigenspace, we know that the minimal polynomial is t minus 1 whole square. Yeah. So it can't be J1 cube, right? So it has to be this thing. Yeah. So it is J21, J1. Yeah. Okay. Is that clear why how we got this? So this part is also ruled out, and then this fits in. Yeah. Because J12 is annihilated by t minus 1 cube, and J11, of course, is annihilated by t minus 1 itself, and in particular t minus 1 square. Okay.
Yes.
How about in the third case? So maybe let's. So what happens in this case? How will the matrix look like? The Jordan form look like?
J12, J12, J2 and J21.
J12, J12,
J21.
J21. This is or okay. Okay, so you are ruling out. So there are two possibilities. You are saying, yeah. What is the or part?
J12, J11, J11, J21.
J21. Yeah. So J11, J2. Yeah. So can is both are possible, or can you rule out one of them? What's your guess? Both are possible or not? Yeah, so to check whether both are possible, you just look at. So it's these things are easy to decide. You look at this matrix, yeah. Calculate this characteristic polynomial. The way you have written, we have written the characteristic polynomial is going to be t minus 1 power 4, t minus 2. And the minimal polynomial of this matrix is t minus 1 whole square times t minus 2, right? And same with this matrix. The characteristic polynomial is t minus 1 whole power 4, and the minimal polynomial is going to be t minus 1 whole square t minus 2. Yeah. So both the matrices are possible. I mean, if A is this matrix, then also I mean the Jordan form is going to be this. Jordan form is unique, right? And I mean up to maybe interchanging the blocks, it is unique. And so both are possible. So you see, so in many cases, the minimal polynomial and the characteristic polynomial helps you fix the Jordan block, but it need not be always possible. Yeah. So in some situations, you need more information from the matrix. So just the minimal polynomial and characteristic polynomial are not enough. Okay. So you need sort of the complete decomposition in some sense of the yeah. So there are other invariants which are not so easy to compute, but you can meaning you can define them. And so if you have that complete list of invariant, then you can sort of determine it. Otherwise, it's not so easy. But so this problem arises in 5x5 matrix. If you are given a 3x3 matrix, I don't think you will have this problem. Yeah. So 3x3 matrix, just from minimal polynomial and characteristic polynomial, you should be able to determine the Jordan form. Okay. 3x3 matrix over complex numbers. Okay, so both in this case, both cases are possible. So is this okay? Why these two are the possibilities? Yeah, and Yeah. So it has to be one of these two. There is no third possibility. Yeah, that is also clear, right? Because I mean, you can't have J13 or J14. Yeah. So if I want J13, can you give me a minimal polynomial and the characteristic polynomial so that I have a block J13 of degree? So characteristic polynomial of degree 5. So maybe yeah. So tell me CH AT. So you have to give me numbers, yeah, exponents of these two, and PAT, exponents of these two, such that there is a Jordan block J13. What exponent should I put? And A is a 5 by 5 matrix. So you understand the question, yeah? I want J13 as one of the blocks. So J13, remember we discussed what it looked like, yeah? So this is J13. So what should be the exponents?
Sir, I don't think the exponents are uniquely determined.
Yeah. But give me one example is what I'm trying to say.
3, 2, 1.
Say that again. So you are giving me the exponents of minimal polynomial or characteristic polynomial? Yeah, tell me. Maybe with the minimal polynomial first. I think it's easier to figure out first with the minimal polynomial. So what should be the exponent of t minus 1?
3.
3, right? Because you want J13 to appear, so it has to be 3, yeah? And then let's not worry about this. So this T2 doesn't matter, yeah? Anyway, we want J13. We don't really care about this thing. And then the characteristic polynomial has to have a T minus 1 cube at least, yeah? So it must be 3 or 4, yeah? So you can put 3 and 2 or 4 and 1, yeah? So either will work. So if you put this 3, 2, then here t minus 2, the exponent of t minus 2 could be 1 or 2. Yeah, it doesn't matter. So for instance, I can put this. Yeah. So in this case, the characteristic polynomial and the minimal polynomial are same, right? So in this case, okay, so how will the, so what are the possibilities for Jordan form in this case? So I guess we already decided J13 has to be there, yeah? What else should be there? So what should be there?
J22.
J22, yeah? So there is only one possibility, yeah? So in fact, you can show that when the characteristic polynomial and the minimal polynomial are same, then also you can determine the Jordan form, yeah? There is only one possibility, which is for each for each eigenvalue there will be only one Jordan block. Yeah. So maybe this is one can put it as a homework. If CHA equals PA, then the Jordan, then find the Jordan form. Determine. So I told you what the answer is, but you prove it, yeah? Okay. Okay. So yeah, I want to separate it a little bit. Yeah. So I think we have discussed enough for the Jordan form. Now I think you'll be comfortable figuring out Jordan form of various matrices. So let's try to understand some other. So you see, Jordan, the way to figure out Jordan form was to find a right kind of basis. Yeah, basis of the generalized eigenvector. So if you have some nice structure to a basis, then it is sort of easy. It tells you something about the matrix. Yeah. So say if V is a linear operator of V, and suppose there exists a V in V such that this forms a basis. Yeah. So V is this capital V is n-dimensional vector space, and suppose this form a basis of V. Then what will be the matrix of V with respect to this basis V? So see, say that again.
The elements on the diagonal and the subdiagonal.
Yeah, so the subdiagonal.
Everything else is zero.
Yeah, so what happens is, so phi v, is going to be, so you'll have to write it as linear combination of this. So the coefficient of v is 0, coefficient of phi v is 1, and the rest is again 0. Yeah. So that tells you that the first column has to be 0, 1, and then 0, 0, 0. Yeah. So this will happen for the first n minus 1 vectors. Yeah. So for the first n minus 1 vectors, you will get so 0, 1, and so on. Yeah. So there is a subdiagonal, and this is going to be, but what, because of this fact that phi of phi n minus 2v is so all zeros, and the last one is 0v plus 0 phi n minus 2v plus 1 phi n minus 1v. Yeah. So this is what you get. But what happens to the last one, phi of phi n minus 1v? This is phi nv. Yeah. So this is this you don't know what it looks like, right? So it's going to be linear combination of something. But we know that it is going to be a linear combination of these things. Yeah. Linear combination of v, phi v, phi square v, because that forms a basis. We have figured that out. Yeah. So that tells you that there will be some column whose entries you don't know. Yeah. So can you think about what that column could be? So let's say it is phi n v is let's say b0v plus b1 phi v b n minus 1 phi n minus 1 v. Yeah. So this is, if this is how it looks like, then it is going to be b0 b1 up to bn minus 1. Yeah. Bn minus 1. This is how it looks like. So can you guess what these BIs are from the matrix, from the linear operator phi? Yeah, exactly. So yeah, so this so the point is, if you consider the characteristic polynomial, yeah, so So you look at this this phi n minus. So it's related to the characteristic polynomial. It's not really. So you consider bn minus 1, phi n minus 1 minus b1 phi minus b0 identity and evaluate it at v. Yeah, then you get 0. Right? That is what the previous equation. So this equation implies this equation. And of course, if you take, so once for v it is 0, then anything is a linear combination of these. So it will be true for phi v as well. Yeah. So if it is, this is 0 for v, if you apply phi here, you can pull out a phi. Yeah. And so this is true. So this implies that this so maybe this is true for phi for iv for all I. Yeah, because I can pull out this phi for I, right? So and these phi for iv's form a basis, so it will be true for everything, right? So this tells you that for every vector. So this tells you that phi for n minus bn minus 1 phi for n minus 1 minus b1 phi minus b0 I restricted to v is 0, or this is the 0 endomorphism. Restricted to v is not needed here. Huh? So let's just get rid of. Is the zero endomorphism? Yeah. So not just on v, but it is 0 on the whole thing. So that tells you that if you consider the matrix, consider the polynomial pt, let's not say, let's say ft to be t power n minus bn minus 1 t power n minus 1 minus b1 t minus b0, then phi satisfies this. Yeah. So that tells you that the minimal polynomial, so the minimal polynomial has to divide it, but the point is it's also, the v has dimension n. Yeah. So phi is a linear operator on an n-dimensional vector space. So this is actually going to be the characteristic polynomial. Yeah. So yeah, so that requires a bit more argument. So we know that PT, P phi t divides FT. And so for the other thing, you'll have to use the fact that this forms a basis. Yeah. So this forms a basis means there can't be a smaller degree. If there is, if there is a smaller, yeah. So in fact, the minimal polynomial in this case is the characteristic polynomial. Yeah, because if the minimal polynomial has smaller degree, then you can find a linear. You can, if you degree say m. Yeah. So if p phi t degree p phi t is m less than n, then v phi v up to phi m minus 1v are linearly independent, but phi mv, this will be linearly dependent. Yeah, because pt has degree m, so there is a linear dependence between these things. Yeah, or linearly dependent, contradicting our hypothesis. Contradicting the hypothesis. Okay. So that tells you that P phi t is a degree P phi t is n, and hence so I mean characteristic polynomial it has to be the same, is of degree n as well, and hence they are the same. Yeah. So this is a special condition. I mean, this doesn't happen for for instance, this forming a basis tells you that minimal polynomial and characteristic polynomial are same. Yeah, and in that case, you can the matrix of phi with respect to this particular basis, you can just read it out from the characteristic polynomial. Yeah. So this is called the rational form. So I'm not going to talk too much about it. Rational form of phi. Okay. So there can be, I mean, so one can define rational form for linear operators where this is not necessarily true. Right? The characteristic polynomial and minimal polynomial may not be same, but that requires a little more analysis and sort of requires structure theorem. So let's not worry about it. But when they are when the characteristic polynomial and the minimal polynomial are same, then you can sort of then you can find such a v, yeah, such that these are linearly independent, and then you can compute the rational form, okay, of the matrix. Okay, so the idea of all this thing is to figure out good a good basis vector or good decomposition of the vector space V into subspaces which are phi invariant. Okay, and which allows you to find blocks of bases and write basis vectors and so on. So if you find good basis vectors, then the matrix becomes simpler, and then it is sort of easier to understand the linear operator in turn. Yeah. So it goes both ways. So if you understand the linear operator better, then it results in a simpler matrix. If the matrix is simpler, then you can do a lot of analysis much more easy. Okay. Any questions or comments? So this time our page became too big, but it's okay. We were only dealing with examples. Yeah. Okay, so last time I also told you I'll discuss a little bit about isomorphism theorem since you guys haven't seen it. I mean, it makes more sense for modules. That's why probably it's not. But I mean, it makes sense here as well. Yeah. So let me. Yeah. Let me discuss a little bit, and then we'll see. Yeah. So did we talk about? Did we talk about quotient spaces? So if let V be a vector space and W contained in V be a subspace, then we can consider V mod W. Yeah. So V mod W is, I mean, as a group, you know what it is. Yeah. So what is this? Do you know what this is as a set? Yeah. So you look at cosets. Yeah. So for instance, left coset V plus W, V in V. Yeah. So of course, V plus W is equal to V prime plus W if V minus V prime belongs to W. Yeah. So this is how. So it's a as a set, it looks like this, and then this is a vector space. Yeah, it's a group together, and so V mod W is a group with respect to usual addition. Yeah, and a vector space as well. Yeah, so what is the vector space? So I'll have to tell you how the field acts on it. So lambda times V plus W is, let's say A, forget about lambda, yeah. A times V plus W is AV plus W. You define it this way for A in the base field F. So over F. And then this is, so then you can check that with this operation. So with, so this gives V mod W vector space structure. Yeah, so this is how you sort of think about a vector space, right? It's a Abelian group together with multiplication coming from the field. Yeah, so this is the, and then you'll have to verify all the axioms. Yeah. So V mod W is a vector space with this kind of thing. So maybe let's talk about some isomorphism theorem. So this is called the first isomorphism theorem. So this is so have you seen this in group theory? Isomorphism theorems? How many of you have seen it in group theory, isomorphism theorems? Oh, okay, no, none of you. Okay, so we'll do it in groups case as well. The theorem is neater in the vector space. In the group theory, you'll have to do a little more thing. So maybe it's a good warm up. Yeah. So let phi from V to W be a linear map. Okay. Then what does isomorphism theorem tell you is that you can get an isomorphism induced from this phi on some certain other spaces. Yeah. Then V mod kernel phi is isomorphic to image phi. Okay. So if I state it this way, then this is sort of trivial, yeah, because meaning something which you have already seen, because we know that the dimension of V is same as dimension of the kernel of V plus the dimension of the image of V, yeah. So this is something which we saw long back, right? And okay, so maybe it will be clear. So the point is, what is the dimension of V mod W? Yeah, so maybe I'll put this as a homework. Yeah, dimension of V mod W is dimension of V minus dimension of W. Okay, so maybe you can try to prove this. Okay. So so from that theorem, we know that any such space, two vector space of same dimension are isomorphic, right? So V mod kernel phi has same dimension. So we know that dimension of V is same as dimension of kernel phi plus dimension of image phi. Yeah, from that. So that tells you V mod kernel phi has dimension of V minus dimension of kernel phi, which is same as dimension of image phi. Yeah. So they have the same dimension, then they are of course isomorphic. Yeah, but this theorem is stronger than what it says. So I'm not just saying that these two are isomorphic. I'll tell you the map, which is the isomorphism as well. So the linear map phi bar, which I'll define phi bar of v plus kernel phi. So our typical element here looks like this, yeah, is phi v. Huh? So if and then the linear map this is well defined. So it's not clear a priori that it is well defined as well, yeah, because I'm defining it so I'm taking a left coset and I'm defining it not in terms of the left coset but a representative, right? V plus kernel phi may be same as V prime plus kernel phi, yeah. So and then if I take a different representative V prime, then one has to show that phi V and phi prime, phi V prime are same, yeah. So one has to also check that it is well defined isomorphism. And it's an isomorphism. Okay, so this is the first isomorphism theorem. So not only we are saying that this is isomorphic, which you can just check by counting dimension, but we are saying that this particular map is an isomorphism. Yeah. So you will see that the same theorem will be true in the group theory case as well. Yeah, when we start doing group theory, and the proof is also sort of similar. So let's see a proof of it. So is the statement clear what we are trying to do? So phi is a linear map between two vector spaces V and W. Yeah, and we are saying that the map what we are defining phi bar is a linear map and it's an isomorphism between V mod kernel phi. And so let's just see that it's well defined first, so that we have a map, and then we will see that it's linear and it's an isomorphism. Yeah. So let's say well defined. Yeah. Why is this phi bar well defined? So that V plus kernel phi equals V prime plus kernel phi for V prime in. So it's possible, right? So we can have two elements in V prime such that the two cosets are same. Then we'll have to show that phi. So if I'm defining phi bar of V plus kernel phi is phi V, then I have to show that phi V is same as phi V prime. Yeah. So want to show phi V is equal to phi V prime. So if I show this, then the map is well defined. Yeah, it doesn't depend upon the choice of the representative. So let's see this. So so you look at, so V plus kernel phi equals V prime plus kernel phi. What does this imply? V minus V prime is, where does it belong? Is in kernel phi. Yeah. So so now that tells you that phi of V minus V prime is, it belongs to kernel phi, means it must be 0. Yeah, that is the definition of kernel phi, which implies PV equals. Okay. So it's basically more or less the definition, essentially. There is no trickery involved. Yeah. So that tells you that this is indeed well defined. Yeah. So and then so hence phi bar is from V mod kernel phi to W is well defined. So of course, if W is bigger than image of phi, then it is not going to be also image of phi is equal to image of phi bar. Yeah, by definition of phi bar. Yeah, anything which is in the image of phi is also in the image of phi bar. Right? Because if W is little w is an image of phi, that means little w. So so this is clear, right? Because if W belongs to image phi, implies W is phi V, implies W is phi bar of which element? V plus kernel phi. Yeah. Right. So that tells you that and it's reversible. Yeah. So if W is so which implies W belongs to image phi bar. And of course, if W belongs to image phi bar, then W is this for some V, which implies W is phi V, which implies W is in. Yeah, so they have the same images. And phi bar is linear. Yeah, so check. So phi bar V plus kernel phi plus V prime plus kernel phi. So these are the two elements. These are the you start with two elements and you show that is additive, right? That is what you'll have to show. So what is this? By definition, this is phi bar of. So the sum of these two things, these two left cosets, is precisely V prime. This is how. So I'm assuming you know what how the operation group operation works on left cosets. Yeah? So this is how it works, and this by definition is phi V plus V prime, which is phi V plus phi V prime, which is precisely phi bar of V plus kernel phi by definition of phi bar of V prime plus kernel. Yeah. So since you haven't seen first isomorphism theorem, I'm doing all the detail, everything in complete detail. So you see that phi bar is additive, and it behaves well with scalar multiplication is the definition. Yeah, whereas sorry, it's not the definition. Yeah, so let's so the second thing you'll have to check is phi bar of A times V plus kernel phi. I mean, it follows from the definition of how this works. So for A in F and V in V. Yeah. So this multiplication we saw is just we multiply A to V and that's it. Yeah. So this is by definition of how V mod kernel phi is a vector space. We know that this is AV plus kernel phi. So this is how the field element multiplies. And this by definition of phi bar is just phi of AV. Yeah, and phi is a linear map, right? So you'll have to use that fact. So this A pulls out. So it's A times phi V. Yeah, which is A times phi bar of V plus kernel phi. Yeah, so this proves that and that phi bar behaves well with respect to multiplying by the field elements. We can pull out the field element. So these two together proves that phi bar is linear. Yeah. Okay. And so phi bar is surjective on image phi by definition, right? So all you have to check is that phi bar is injective. Yeah. Also check phi bar is injective. So this I'll leave it as an exercise for you because I'll give you an alternate argument which applies in vector space cases. But you can do it directly by checking that the kernel of phi bar is precisely the zero element of V mod kernel phi. Okay. But the alternate argument is that the dimension of V mod kernel phi is same as the dimension of image image phi. Yeah, that is what we argued initially, why these two spaces are always going to be isomorphic. Yeah, so these two have the same dimension and this map is surjective, so the kernel has to be trivial. Yeah, so it has to be a bijection. Yeah, so a linear map which between same dimensional vector space is an isomorphism if it is surjective. Right, you don't need to check both injectivity and surjectivity if the dimension of the two spaces are same. Okay, so you can use that or directly prove that it is indeed injective. So is this clear? Any questions on the first isomorphism theorem? No. Okay. So then there is a second isomorphism theorem, which I'll have to recall what the statement is. So they all sort of follow from each other. Yeah. So second. So first isomorphism theorem, from there you can deduce everything. Second isomorphism theorem by some. Yeah. So what is the second isomorphism theorem? Yeah, so the third one is easier to remember. So that's why I'll write down the third isomorphism theorem as well. And then we'll try to recall the second isomorphism, third isomorphism theorem. So you have chain of vector spaces, yeah? So U is contained in W is contained in V, okay? Vector spaces over F, yeah? Then what the third isomorphism theorem says is that V mod W is isomorphic to V mod U. So V mod U is a vector space, yeah? And this contains W mod U as a subspace, yeah? So these are all left, V mod U is a vector space consisting of all left cosets of U, yeah? With entries in V. And since W is a subspace, all left cosets of U which has representatives in W form a subset, yeah? And hence you can ask whether it's actually a subspace. So W mod U is a subspace of V mod U, and hence you can take a quotient again. So what this theorem says is that V mod W is isomorphic to V mod U mod W mod U, yeah? So this is sort of, yeah, so I mean, again, using the dimension theorem, dimension argument, this is sort of clear, yeah, because dimension on the left is, so dimension of V mod U is dimension V minus dimension U, and dimension of W mod U is dimension W minus dimension U. So if you take their differences, that will be the dimension of the right-hand side. So dimension of the right-hand side is dimension V minus dimension W, yeah, which is equal to dimension of the left-hand side. Yeah. But again, the isomorphism is sort of natural in the sense that there is a map from, yeah, so, okay. So let's discuss third isomorphism theorem. We'll come to second isomorphism theorem later. Yeah, so there is a map. So So first of all, I mean, there exists an isomorphism is clear, but I'm not saying that. So the statement is again stronger than there exists an isomorphism. I'll tell you what the isomorphism is. There is a natural isomorphism which exists. Yeah, this is not useful in the linear algebra setup, but it will be useful in group theory, for instance, or maybe other things you study, modules, etc. It will be useful. Yeah. So see, V mod U to V mod W, there is a map, linear map. So let's call this map Q. Okay. So what is the linear map? What should be the linear map Q? What is the natural linear map? You can do. If you have to guess, where will you send V plus U? Yeah, make a wild guess. Yeah, what could it be?
V plus W.
V plus little V plus W. Yeah. This is I mean I said it's natural. So the only natural thing is this. Yeah. So Q sends V plus U to V plus W. So you'll have to check that this is first of all well defined and linear and so on. Yeah. So linearity is will be straightforward. We just check because it's close to identity map. Yeah. So identity map we know is linear. So let's just check it's well defined. Yeah. So let's say V plus U is equal to V prime plus U. So what does that tell us? This implies that V minus V prime belongs to U. Yeah, this is what the definition of these two being equal is. But this U is of course contained in W. Yeah, so this is contained in W, right? So this implies V plus W is equal to V prime plus W. Yeah. So that tells you that Q is well defined. Yeah. This is what we'll have to check. Yeah. So if you take two different representative, then it leads to the same target. Yeah. So V plus U goes to V plus W. V prime plus U goes to V prime plus W. But if V plus U is equal to V prime plus U, then V plus W is also equal to V prime plus W. So that left coset is going to the same left coset. Yeah. So the two left, if the two left cosets of U are same, then it's going to the same left coset of W. Okay, so Q is well defined. And what is kernel of Q? Kernel of Q means those elements which go to the zero element of V mod W. What is the zero element of V mod W? Is so V plus so by definition is V plus U such that Q of V plus W is the zero element. Yeah. So what is the zero element? V plus U, sorry, not V plus W. Q of V plus U is the zero element. But what is the zero element of V mod W? Yeah, say that again.
0 plus W.
0 plus W. Or sometimes people just write it as W. Yeah. So, but Q of V plus U is just V plus. So this is just saying that is V plus W should be same as 0 plus W. Yeah. Which means what can you say about V? V is an element of W, right? V minus 0 has to be in W. So V is an element. So kernel Q is precisely V plus U. V belongs to W. Yeah, which is precisely W mod U. Yeah. right? So the whole thing is V mod U, and kernel Q is W mod U. Yeah. So by first isomorphism theorem, you apply first isomorphism theorem to this linear map. Yeah. So by first isomorphism theorem applied to Q, you get that V mod U mod W mod U to is isomorphic to the image of this thing, but the image is going to be the whole thing, yeah, because of the way it is defined as V mod W. Yeah, every element is in the pre-image of the right thing. Yeah? And the map by induced by Q, so it will send V plus U plus V mod U. So it looks complicated, but we are doing the right thing. Yeah, goes to V plus W. Yeah, this will be the map. Right. So this Q bar is precisely this thing. Okay. So we are not just proving that these two are isomorphic, but we have given you the right isomorphism. Yeah. Then there is a natural isomorphism where V plus U, the left coset, V plus U plus W mod U goes to V plus W. So that's the third isomorphism theorem. Now I'll have to recollect what the second isomorphism theorem is. Yeah. So I guess there is a vector space V, and there is a subspace W, and there is one more subspace. So U is also a subspace of V. So V vector space over F and these two happens, and so U and W are subspaces. Okay, and then the statement is U plus W. So the subspace generated by U and W is again a subspace. Yeah, it need not be a direct sum. Yeah, it depends upon what I mean. They may have an intersection, but it's a subspace of V, right? Internal direct sum. Mod one of them, let's say W, is isomorphic to let's say U mod U intersection W. Okay. So if you consider U plus W, it's a subspace of V and it contains W, yeah, as a subspace. So left-hand side makes sense, yeah. And again, U is a subspace of V and U and W are subspaces of V, so the intersection is again a subspace. So U plus U intersection W is a subspace and is contained in U, so it's a subspace of U. So again, the quotient right-hand side makes sense, yeah. And this is an isomorphism. And again, this is a natural isomorphism. So you can give a map from one to the other, and so which direction is it easy to give a map? Yeah, so this one, maybe I'll leave it as an exercise, and I'll give you a map and you complete it, yeah. So you give a map from U to U plus W mod W, yeah. Where should you send an element? Let's call it X, yeah. So let's take X here, and you send it to X plus W, yeah. So this, of course, by definition, I mean, here you don't have to check it's well defined, yeah, because I'm defining it in terms of X. It's just the quotient map, yeah. So this let's call this Q, yeah. So you check that. So the kernel of this map is precisely U intersection W, and the image is the whole thing. Okay. So this is what you like. So that will prove that this is isomorphic. Yeah. So here the dimension count is not going to help you because you don't know what U plus W looks like, right? So meaning it's not an internal direct sum. So calculating dimensions are not so simple in this case. So here you'll have to prove that the kernel is precisely U intersection W, and hence by first isomorphism theorem, you have an isomorphism from U mod U intersection W to the image of Q, and then you also have to check that the image of Q is the whole thing. Okay, so this is homework. Okay. So maybe this is where we can stop. So let me first stop recording.